And it's day 4, and we are on the home stretch. For today, we're going to talk about generalized survival models, which are also known as flexible parametric models. We're going to spend an extended time talking about non-collapsibility. We're going to do a bit of a review on nested case control studies. We'll describe standardized mortality and incidence rates, and we're going to talk about some possible biases in survival analysis when we're reporting on survival analyses. So, what about smoothing? We're going to be using splines for a few things. So in Poisson regression, instead of modeling time as a step function, what we could do is do fine time splitting, and then sort of like we'd like to actually sort of do a smoother across the time intervals rather than using many parameters. One of the approaches for doing that smoothing is to use splines. And splines are a way of modeling continuous variables in a flexible way in a number of different regression contexts. For cubic splines, what we do is we have knots, which is a fancy term for saying values that split up the x values into intervals. And then for the knots, that the user has to either specify the number of knots, such as 3 or 4 or 5, and then there'll be automatic knot placement, such as using quantiles of the event times, or that the user has to specify the number and the placement of the knots, or we could just sprinkle in many knots and then try and find a function which fits nicely, but which is not too wiggly, using penalized regression. The user also has to specify the type of cubic splines, and if we do B splines, then they're cubic before and after the first knots, and that's implemented in the BS function from the splines package, or natural splines, which are linear before the first knot and linear after the first knot, and that's implemented in the NS function. There are other splines, including periodic splines, Q models, which are flat after the first knot, and so on. But we'll focus on, we'll mainly use natural splines. A picture is worth 1,000 words. What we've done is we've generated some data, which are the circles. Then we've specified knots here, here, and here, and that could have been chosen just to sort of separate out the data. Then the knots form intervals. In this first interval, what we do is we fit a cubic, and then in the next interval, what we do is we fit a cubic, and fit a cubic. But if we're looking at these, they don't look that nice. So the first thing we do is say, let's actually have that they join up here, here, and here at the knots. And then what we do is we now find, yes, they're joined. That looks quite good there. That looks okay here, but it looks a bit weird here, because the slope coming from the from this side is quite different to the slope coming from this side. What we can do to make this look nicer is say we want the slopes to be the same at the knots here. So then this is assuming continuous first derivatives. Now the slopes are the same here, slopes are the same here, and here. But the rate of change, it looks very flat here, and then it's changing more quickly here. And would actually look slightly nicer if we had both continuous first and second derivatives. And then if we do that, it starts to look quite pretty to the eye. So we've got continuous first and second derivatives, which are called B-splines, and I think that is a reasonably good description of those data. So we can use splines to model for the baseline hazard, and one approach would be to use Poisson regression, split finally for time, and then use splines for smoothing. This works especially well for multiple timescales. An alternative approach is to model for a transformation of survival, the so-called generalized survival models or flexible parametric survival models. And the most common of these models is done on the log cumulative hazard scale. So that means if log of the cumulative hazard at time t given covariates x is some smoother for log time plus a linear predictor, where s is the smooth function, such as using natural splines. Once we've got the cumulative hazard scale, we can do two things fairly easily. We can calculate survival, which is equal to exponential of the minus cumulative hazard, and we can also calculate the hazard by differentiation. So the derivative with respect to time of the cumulative hazard is equal to the hazard, and there's a fancy formula here. What we can do is for a unit change in one of the exposures, divided by the hazard for the baseline, we plug in some math, we simplify things, that cancels out, then we end up that the hazard ratio for a unit change is equal to exponential of beta. So we have a proportional hazards model. So one of the elegant approaches, aspects of this approach is that we can directly model for interactions between covariates and between covariates and time. And that allows us to model directly for non-proportional hazards. So what we can have is you've got your baseline for time, you've got your time fixed effects, and then you've got interactions between some of the covariates and smoothers for log time. And then we can directly estimate time varying hazard ratios, which is beautiful. We've implemented both parametric and penalized generalized survival models in the RST-PM2 package on CRAN, but there's also the FlexServe package on CRAN and the ST-PM2 command in Stata. The parametric models default using natural splines for the smoothers by time, and then the investigator needs to specify the degrees of freedom by using an argument df equals 3 or 4 or 5. The penalized models do not need to specify the degrees of freedom, and then these models are closely related to generalized additive models, and you can actually do generalized additive models for Poisson outcomes, which is another very elegant approach. Showing some code, we create an object called fit4 from ST-PM2 with the survival time in months for a cause specific death, adjusting for sex, age group, and calendar year of diagnosis from the colon data restricted to localized cancer. And then we need to specify the degrees of freedom for the baseline, and 5 is reasonably generous. And then we compare the coefficients from the ST-PM2 with Cox, Poisson fine, and Poisson. And what we find is that ST-PM2 looks reasonably similar to these other approaches. So the hazard ratios from ST-PM2 are very similar to those from a Cox model and from a Poisson model. Since the baseline hazard is modeled, it is easy to include non-proportional hazards and interactions, and that the time scale is included as a continuous variable, so there's no more implausible step functions. It's also easy to present the results using graphs, and this approach is very good for doing predictions and extrapolations. So what we do is we take the colon data and we add in some binary indicators for distant and regional. we drop the unknown stage from the factor, and then remove the unknown stage. That's just setting up some data, and then what we do is we do a fit for STPM2 for sex, and then an indicator for regional and an indicator for distant from using the known data. We use 5 degrees of freedom, but then we also allow for time varying effects, 3 degrees of freedom for regional and 3 for distant. And then we can plot from this fit the hazards from data which are males for distant is equal to 1, and then we set up the X label. We can also do lines with confidence interval for regional and also for localized. And then this shows us the hazards by time for distant, regional, and localized stage, allowing for time for different baselines. Now, the beautiful thing here is we can also fit for time-dependent hazard ratio, comparing the distant with localized colon cancer. And this will actually be true for both males and females, because it was a man effect for sex. So then what we have is we get a hazard ratio out. The baseline is for localized, and then what we do is we increment the variable for distance. So this will go from 0 to 1. And then we sort of find that there was an initial increase here in the hazard, and then a decrease here, and actually it drops below 1 here. So I think this is a beautiful plot. We can also plot this with a log on the y-axis, and this shows much closer what the shows much more clearly it dropping below 1 here. So what we can also do is plot for survival differences. So again, we start off with males. Now that this is important because it's not a hazard ratio, and then we sort of start off with localized as the reference, and then we sort of say instead of using the var equals distant, we can instead do something which is much more explicit and say exposed, which is a function taking some data, and then we transform the data where we change distant is equal to 1. So this could also have been done as being shorter, would be var equals distant. That will actually do the same thing. The nice thing about using the exposed is that you can do virtually any contrasts. You could add, you could increment different values, or you could change multiple values at the same time. So, and then this shows that this shows the survival differences here, and then what we find is that the cumulative, that the survival difference peaks here, and then because the hazard for distant drops below 1, then this starts to rise here. So, and also the hazard is getting closer. This shows distant versus localized, and then this is regional versus localized, and this shows that the nadir is around probably 7 years. We can also do time-dependent hazard differences, doing much the same approach. So if we go back to the previous slide, if you change this to being HDiff, then we can actually get hazard differences. Although I think from a causal perspective, the survival differences is much more important, and probably the hazard ratio has got a nice interpretation. Okay, let's take a bit of a step back and think about what happens with proportional hazards models with unmeasured covariates. And what we're going to do is going to assume that you've got two covariates, X and U, and that assuming that they're independent, such as from a randomized controlled trial, where say X could be a treatment effect and U could be other covariates. It also means that U is not a potential confounder for X. So U could be just a bunch of other things which are associated with the outcome, but they're not assumed to, they're assumed to not confound. Intuitively, the initial events for the Cox model will be randomized or independent, which will have a nice causal interpretation, but later events are based on factors that may affect survival, which could lead to a bias. So we're going to say here may lead to a bias. And what we do is we initially consider a causal diagram for survival to time t, and then survival to time t plus delta. So what we have is X is assumed to affect survival to time t. U is assumed to affect survival to time t. X is assumed to affect survival to time t plus delta, and U is assumed to affect time survival to time t plus delta. X and U are not associated in this causal diagram. And if we were to model for the hazard, then that the hazard here means that S of t is associated with S of t plus delta. So this could cause problems. Now, to simplify this, if we consider how X affects survival at time t or time t plus delta, then we do not open the path through U, and we can get causal estimators for X. So there's no path here, so we actually wouldn't need to model for U here or here. We could just look at the effect from X to survival at this time, or X at on survival at this time. So this suggests that survival differences or ratios can have a nice causal interpretation, provided that there's no unmeasured confounders. This causal diagram. If we are modeling for the hazard and we adjust for X, then we implicitly adjust for S of t, and that's acting as a collider. And importantly, that opens a non-causal path from X, from here to here, from here to here, and then all the way around here. And unless we can actually close the path by modeling for everything that's associated with survival, which will be very difficult in practice, then we will not be able to get a causal estimator. And I should emphasize that this is generally true for the Cox model, but it won't be true for other models, including Olin's additive hazards model. So an alternative approach would be to actually use simulation with an unknown example. So what we do is we sort of say, we know what the answer should be. Can we estimate the answer from the available simulation? So we start with a known truth, and then see whether we can estimate a known target parameter from simulated data. So for this simulation, what we do is we assume that X is binary, and then we assume that U is normally distributed. And what we'll do is assume that the time to event has a constant hazard, so it means it's going to be exponential, and assume that the rate varies by both x and u. It's not terribly important, but we'll also assume that c is uniform and that they assume that the censoring is independent of t. So what we do is we sort of say here, is we've got x is independent from u, and assume that both of these are affecting time t. And then we've got censoring, which is assumed to be independent of everything else. And then the minimum of the event time, so the minimum of these two is equal to y, and if t happens first, then delta is equal to 1, otherwise delta is equal to 0. And we also assume that in the hazard formulation, the coefficient for u is 1, and the coefficient for x is 1. So what we have, x is Bernoulli with probability of half, so it's just basically a coin flip. U is normally distributed with mean 0 and a standard deviation of 3, and then t is assumed to be a constant hazard with respect to time, but it varies, so it's exponential of -5 plus x plus u, and then c is just assumed to be uniform, but that's not important. So we sort of set the random number seed. We do it for 10,000 individuals. We do a bunch of coin flips. Then this is normally distributed. Then this is constant hazard with this rate. And then this is uniform between 0 and 10. And then the actual observed event times is the pairwise minimum of the t and c, and then the delta is when t is less than c, and then we output a data frame with observed time y, covariate x, covariate u, and the event indicator delta. So that's how we simulate. And what we should be trying to do is get out a coefficient of 1 for x and a coefficient of 1 for u. Right, now how would you model with if you knew both covariates x and u? And then how would you model with just covariate u, sorry, with just covariate x when u is unmeasured? Now for these particular data, there are many ways that you could model for what are comparatively simple data. So what we could do is we could do Poisson regression, we could do Cox regression, and we could do flexible parametric solve models. If we do that, so what we do is we do a GLM for the delta is the outcome, adjusting for x and u with using y as the person time. So we do an offset of log of the person time from our data set for Poisson. Could also do a Cox for survival time y with the event indicator delta, adjusting for x and u. And then the Cox, so the STPM2 is almost identical, but we also need to specify the degrees of freedom for the baseline. And then this is fancy code to give this table where we want to look at the x coefficient. And these are all very similar and very close to 1. And then the standard error here is slightly smaller because this is actually the correctly specified model where it's assumed to be piecewise constant. So, but in all of these, we've adjusted for both x and u, and we get pretty close to the right answer. So, in summary, all three models estimate the target log hazard ratio, which is approximately equal to 1, and the standard error for Poisson is similar to and slightly smaller than those for Cox and STPM2. Now, modeling only for X without U. What we do is basically the code is the same here. The only difference is that we're only adjusting for X. Then we've got the same code to be able to pull that out, and whoa, this is very, very different. These values, so this is not approximately equal to 1. So these are quite different. So when we don't adjust for U, now don't forget, U is not a confounder. U is not a confounder. It is just a covariate which is associated with the outcome, and it's strongly associated with the outcome. And then what we find here is that this does not give us values, that these values are actually about half of what we would expect. So these are called marginal hazard ratios because we're basically we're estimating the marginal without U. That in this case they can be quite different to the conditional hazard ratios from the previous models. As an exercise, see exercise 14, we can investigate whether the hazard ratios are time varying for the STPM2 models for both X and U or with only X. Now this is a bit technical, I won't take too long. So what we do is we do an STPM2 adjusting for both covariates and allowing for a time varying hazard ratio, and it's practically flat, which is not surprising. And what we can do is we can plot the hazard ratio for a fixed U for an increment in X, and then that's basically approximately exponential of 1. So, and then what we can do now is fit a marginal model, not adjusting for U, again allowing for a time varying hazard ratio, and again doing a hazard ratio here for an increment in X, and then we find a very, very strong time varying effect. So the conditional effect is constant, that the marginal effect starts off at a value which is actually quite similar and then declines down towards 1. So the hazard ratio for X with both X and U is conditional on the values for U. For our example, the hazard ratio is constant with the respective time. The hazard ratio for X for the model with only X is marginal, or an average over the values for U. For our example, the hazard ratio starts close to exponential of 1 and is then strongly attenuated. If we fit a marginal model with a constant hazard ratio, then we estimate an average of the time varying hazard ratio. So if we go back to here, if we actually averaged across those, we'd probably get out a value here, which I think is actually close to exponential of 0.5, which is actually what we estimated. So individuals with higher values of X and U are more likely to have an event earlier, so there is strong selection. At later times, the distribution of U and X for the survivors are expected to have lower values. But normally distributed unmeasured covariates U, theory says that the marginal hazard ratio for X will be attenuated. For unmeasured covariate U or unmeasured, the covariate U or unmeasured heterogeneity is also called a random effect, and exponential of U is also called a statistical frailty, which you might hear used. We would prefer to have a model which is collapsible, where we want the marginal estimate without the measured covariates is the same parameter as the conditional estimate. And a related example is for odds ratios, which are also not collapsible. To emphasize, we have assumed that U is not a confounder for X. Consequently, this issue is similar for both randomized controlled trials and observational data. We can reduce the attenuation by modeling for covariates that are not confounders, but we shouldn't need to do this. For proportional hazards, there are two conditions for for hazard ratios that aren't equal to 1, where the non-collapsibility is negligible. So the first thing we can do is we can assume that we've got rare events. So we basically look at outcomes very early on. And I think we also made this the n slightly larger. And then we find that it's not. So this is without U, and without U. And these are much closer to 1. Yay! Also, if there's a smaller frailty, so instead of the random effect being 3, so that was 3. Now we change it to being 1, and then if we do that, then this is much closer to 1. So a small random effect or rare outcomes, and then the Cox can give a causal estimator. So non-collapsibility is less of an issue for rare events and for a small frailty variance. Unfortunately, for small unclustered events, we cannot assess the size of the frailty. So modeling indirectly helps, but we still cannot characterize the unmodeled frailty. Other approaches that we could do is regression standardization. So what we do is we fit a model to the data, and then we calculate standardized hazard ratios and standardized survival differences. So standardized survival, S bar of t at time t is calculated from, what we do is we basically calculate survival at time t given covariates weighted by, and these WI could be just equal to 1, but standardized survival is weights of the predictions across a bunch of individuals. Actually, I think what we do is you do 1 over n. Oh, sorry, 1 over n will just give you the average, and that's the example that we show here. Now, the big question is, how do we do this? What we can do is we can estimate standardized survival under counterfactual exposures. So S bar K here is the average of survival to time t given UI, setting K, say setting X is equal to K. So what we do is we take all of the observations and then assume everyone was exposed and then everyone wasn't exposed. So this shows the example comparing all exposed and all unexposed, and then you average. We can do this in STPM2. These are survival differences. Actually, these are conditional. So this is X plus U. Here, we're looking at survival differences, conditional, and we get this sort of straight line here. We can also do mean survival differences, where new data is the original data, setting everyone to being unexposed, and then we increment the X here. And then this shows this nice pattern here. Instead, what we could do is this is fitting without the, the U with the time varying, and then look at the survival difference, and then the pattern here and here is very, very similar. So that means that the marginal from this model and the standardized from this model tell a very similar story. We can do the same thing with the hazard ratios. Conditional for modeling for both is flat. Standardized for both shows that this is the hazard ratio for x. This is the hazard ratio for x from the marginal and from the standardized. And then, so now we've introduced splines. We can think about how we could use the splines to model for the baseline hazard. One approach would be to use Poisson regression. It's split finely by time, and then smooth using the splines. And that actually works particularly well for multiple timescales. An alternative approach, instead of using Poisson regression, would to be modeled for a transformation of survival and then fit a regression model within a survival context rather than assuming that it's piecewise constant within the time splits. So, and then if we do a transformation for survival, these are these so-called generalized survival models or flexible parametric survival models. The most common of these models is on the log cumulative hazard scale. So what we do is we sort of say that the log of the cumulative hazard at time t given covariates x is some smooth function of log time plus a bunch of sort of standard time fixed linear predictors, where S is a smooth function. And I think the default for the parametric models that we use is natural splines, but we can use other smoothers as well. One advantage of the cumulative hazard scale is that we can easily calculate survival. So that means survival at time t given covariates x is equal to exponential of minus lambda, capital lambda of time t given x from this expression here. So, and we can also calculate the hazard by differentiation, so that the hazard is the derivative of the cumulative hazard, which if we do some math is equal to the cumulative hazard times the derivative of the smoother divided by t, which is not this is not so important. What is pleasant about the log cumulative hazard scale is that by default it gives us proportional hazards. So if we have an increment in one of the covariates, the baseline is x0, and then that's increased by 1 unit. If we do the math, things tend to cancel out, and then we're left with a proportional hazards. What's beautiful about these models is that they extend very easily for non-proportional hazards or time-dependent effects by creating interactions between covariates and splines for time. So the log cumulative hazard is some baseline. It's like an S0 function. It's a baseline smoother plus the time fixed effects plus interactions between smoothers for log time and covariates xj, where j is an index for the time dependent effects, and there could be 1 or 2 or 3 of these. There's not normally many of them. We have implemented both parametric and penalized to generalized cell models in the RSTPM2 package on CRAN. You could also see the FlexServe package on CRAN and the STPM2 command in Stata. The parametric models default to using natural splines for the smoothers, which means that the investigator does need to specify the degrees of freedom. But apart from that, the model formulation should look very similar to Cox. For the penalized models, we don't need to specify the degrees of freedom. And what this does is it actually chooses a smoother, which gives us a reasonable, like a balance between a reasonable model fit, and but you don't want the function to be too wiggly. And these penalized models are very closely related to a model class which you may have heard of before, called generalized additive models, which are like an extension of generalized linear models. And we can also use the generalized additive models with the Poisson data, and that works particularly well for multiple timescales. So, other approaches to address non-collapsibility. What we could do is we could actually use several models which are collapsible. And a popular choice has been Olin's additive hazards model, which if we had a continuous hazard, that the hazard at time t given covariates x is equal to some baseline for baseline hazard plus covariate effects, and it's an addition here and here. These are all additions, so they're sums of the covariates times time-dependent effects beta j. So this actually is a time-varying effect. Although this is a hazards model, the linearity means that the marginal and conditional models are similar for covariates that are not confounders, and it is collapsible. The different exposures are assumed to act like competing events, which are related to Rothman's causal pies rather than proportionally. And this additivity does not seem to hold for some types of events, such as cancer survival by age and sex. These models are implemented and available in the TimeReg package on CRAN, which allow for left truncation and right censoring. What's interesting is that when we actually fit these models, they're reported using non-parametric time-varying cumulative effects. So you have to, in some sense, sort of differentiate in your mind. So that means what we actually get out are estimates of the cumulative hazard, which is expressed as the cumulative baseline. You actually get out this entire term here, and then you get out each of these terms here. And then to actually, if we're interested in this or this, we have to think about differentiating the cumulative effects. Note that this model does not hold for our simulated data. Next, an alternative promise which shows an alternative approach which actually shows considerable promise is to use accelerated failure time models where the variable t is equal to some baseline effect, so baseline time to event variable t naught times exponential of minus beta x, and this is proportionality on the time scale. We have recently developed smooth accelerated failure time models, which allow some flexibility in the survival baseline. So that means what we have is that survival to time t given covariates x is some smooth baseline function times t times exponential of minus beta x. And if you see the RST PM2 AFT function. So our the simulated data, which are exponential, can also be fitted as an accelerated failure time model. So what we can do is using the RSTPM2 package, we can do a fit.xu using the AFT function, using solve time for time y and event delta, adjusting for both x and u, with 4 degrees of freedom for the S0 function. And then what we can do is we can also do the same fit with just x in it, with the same degrees of freedom, and then we can combine these data. And what we find is that when we fit for both variables, this is very, very close to the target, which is -1, because it's minus beta here rather than plus beta. But if we don't fit for the U, which are strongly associated with the outcome but not associated with X, if we don't fit for U, we again get a value which is very close to -1. So that is excellent news. That shows, for this example, collapsibility. You should also note that if you don't adjust for U, your standard error is much larger. But the nice thing is we don't necessarily, we almost certainly will not know all of the variables which are associated with the outcome. So although we lose, this sort of shows that if we adjust for more variables that aren't confounders, we can reduce the standard error, but it doesn't actually improve the point estimate. And we see from this example that the AFT models are collapsible. Right, change the topic. We're now going to talk about likelihood calculations for the Cox model, and then that will lead us on naturally to thinking about nested case control studies. And an important concept for both the Cox model and for nested case control studies is the concept of risk sets. And understanding risk sets is central to understanding risk sampling, such as used for case cohort and case control studies, which we'll present shortly. So the risk set at each failure time is the collection of subjects who were at risk of failing at that time. In theory, only one individual can fail at each failure time, and we can calculate the conditional probability of failure for each for the subject who actually failed. And the partial likelihood function is the product of these conditional probabilities. That's a bit of a mouthful. I think it's probably easier if you sort of think of an example here. So imagine that we have 5 individuals at risk of having an event, and each of those individuals have hazards lambda 1, lambda 2 through to lambda 5, which and those hazards may be different since the individuals have may have different covariate values. Conditional on one of the 5 failing, and in this case we assume it's the number 2. The conditional, what do we got here? The conditional probability of failure for the subject who actually failed is your lambda 2 divided by the sum of lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus lambda 5. Now for a Cox, what we can do is that lambda t is equal to lambda naught times exponential of x beta. We can substitute in for lambda 2 is now going to be lambda naught t times exponential of x2, which is the covariate for the second individual, times beta, divided by the sum, and they've all got lambda naught exponential, and then they've all got different covariate values. And then very nicely, the lambda naughts, they all cancel out. And then what we get is exponential of the x to beta divided by the sum, and the notation here is those are the individuals who are in the risk set R. So R represents those who are at risk of having the event at the time of this event. So it's the sum for I belonging to the risk set of exponential of xi beta. And the likelihood function is the product of those conditional probabilities for all of the observed event times. This gets a little more tricky to write when we've got ties, but for assuming that we've actually got distinct failure times, what we have is that the full likelihood is equal to the product over the events of exponential of the events exponential of the covariate times beta for the events divided by the sum of the individuals who are in the risk set for that jth event of exponential of minus xi beta. And that's actually what is plugged into the sort of maximum likelihood optimizer, and from that we can also get standard errors. There could be further covariates where we could have, say, k potentially time varying covariates. So then the beta I, so xi beta gets changed into, you might have xk here, xjk, and it's possible that these effects could vary by time. If we don't have this, then we don't have time varying effects. And when we do Cox pH without the TT function, then we get this this likelihood, and with the TT function, we're actually sort of saying we're allowing these values to change with respect to time. So note that these calculations do not depend on the underlying failure times themselves. All that happens is that we need to know the risk sets and the covariate value. So we use time here for defining the covariates, but we don't actually use time elsewhere. And although this is not strictly a likelihood, it is a partial likelihood, and actually has all of the properties of a full likelihood. If we do observe multiple failures at the same time and we have ties, then we will need to use an approximation to try and sort of tease apart what would have come first. So, and this is conceptually similar to a matched on time or an intensity density sampling for a case control study. And a Cox partial likelihood is actually almost identical to the likelihood for a conditional logistic regression. The only change is that you put a star here on the RJ, where RJ star is a subset of those at risk. So all the rest is the same. Okay, when fitting the Cox model, we're essentially comparing at every failure time the characteristics of the individual who failed to the characteristics of all individuals who did not fail. So, and we could think of this as a case control study matched on time. And then at each failure time, we have one case and several hundred or possibly more controls. What we could do instead is select, for example, 5 controls per case, and we would not lose that much efficiency, or it could be 10, or it could even be 100. But you could see that that if you get a very large cohort, this could be very large, so far as the risk sets. So these reductions would all be a lot smaller than this here. Our controls are selected from the risk set, and a single individual may be a control at multiple time points, and a control may later become a case. And in this sense, this is a nested case control design, so which is a case control study which is nested within a cohort study. We like these designs because that they allow for statistical efficiency and a substantial savings in cost and time. So, and we may wish, so if it's actually expensive to collect data, this is a really amazing way where you keep all of the data on the cases, and then you sample for the controls. And say it might be expensive to pull records for, say, patients diagnosed with colon carcinoma. So this will substantially reduce the size of the study. So what we would do is that we'd sample from the control sets, and then we'd extract information for all individuals who died, but only a sample of those who did not. Another ideal application is when we've got a population-based cohort, and we're taking blood samples with the aim of studying the association between say, genotype and disease risk. And we store the blood samples, and only after follow-up of the cohort do we analyze the samples for the cases, the individuals who developed the disease, along with a sample of controls. And generating a nested case control study is straightforward in R. But what we'll first do is we'll repeat the full cohort analysis of the localized colon carcinoma data, and then we'll show an example using the nested case control. So what we do is we subset the colon data for localized stage, and then we determine the event as being cause-specific death, and then we do a Cox on 12 time and months for this event being cause-specific death for sex, age group, and calendar period of diagnosis. And then we give it a summary. And then we find that these hazard ratios here. So that's standard. And now what we can do is using the epi package, and then we set the seed so it is reproducible. And then we sort of do CCWC for case control. The exit time is survival time in months. The failure is the event for these data. And then what we're going to do is we're going to include sex and age, but we're going to match on age group with 3 controls per case, and to do this silently, otherwise it gives out a lot of output. And then if we actually look at the tail of this data frame, what we find is we have something called set and map. I think map might be row number, and then these are the times. It shows that you've got this set here, and you got here that there would be another 2 in the set, and then we find that the times are all the same here. The age group has been matched, but sex varies and calendar period of diagnosis varies, and we have the event here. So then we, given those data, we fit a C-logit, which is a conditional logistic with failure, adjusting for sex and year, and then stratifying. So this is like a stratified Cox, but stratifying on sex. So that means the calendar period is going to be partial. So the risk sets in the time of the risk sex is partialed out. So then what we end up with is having these 2 values here, which are comparable to the results from here, sex and calendar period of diagnosis. Here. And these estimates are similar to the full cohort, but the standard errors are, so if you've got the 0.057 here compared with it's quite similar there in the year, but they are slightly larger. So sometimes we only have outcomes for an exposed population and no unexposed population to compare with. And then we sort of can't calculate rates, sort of comparing the exposed with the unexposed. What we can do instead is actually estimate the rate or the number of events in the exposed. and then compare that with the expected rate or expected number of events for a standard population. As an example, we might be just studying disease incidence or mortality among individuals from a given occupation, like maybe farmers or painters or airline cabin crew. Or we could be looking at, say, cancer incidence in a cohort which has been exposed to ionizing radiation. So the standardized mortality ratio is the ratio of the observed number of deaths in the study population to the expected number of deaths if the study population had experienced the same mortality as the standard population. And this is an indirectly standardized rate. We can either talk about standardized mortality ratios or standardized incidence ratios, depending upon the sorts of outcomes that we are working with. So what we, as an example, we may be interested in looking at the hazard ratio of cancer among organ transplant recipients compared to the general population, and there's a nice reference there. Estimation in R. To estimate an SIR or an SMR, we typically assume the expected rates to depend upon the person times split by age, sex, and possibly calendar period. Then we use the surf split function to split up the follow-up time in the same way as we have for the background rates. So if the standard population rates are in 5-year age groups, then we split using the same categories. Then we multiply the expected rates by the person time to get the expected number of events in each category, and then we collapse. And so we collapse to get the total number of observed cases and total number of expected cases, O and E, to calculate the standardized incidence ratio, which is just the observed divided by the expected. And we can also have covariates and do modeling, and then instead of using the log of the person time as an offset, we use log of the expected as an offset. So for an example, with a binary exposure X with collapsed data, so that means, say we had a group where we had observed exposure for some of them, and then say for some that they were exposed, and then the others were not, and then we sort of use the background, the standard population rates, and then the person time to calculate the expected. And in this case, it happens to be 10 and 10, but then the observed were 21 in the unexposed group and 32 in the exposed group. Then those are the data, and then we can do a GLM, Poisson regression, using those data with the exposure, and an offset for the log expected, with the observed as being the outcome. And then this shows that the after adjusting for the factors in the standard population, which could be age and sex, then the SIR would be 1.52 with a 95% confidence interval between 0.88 and 2.64. To show an example which is restricted to only those exposed, I was involved in this study where it's a cohort study of men exposed to household asbestos from the Australian Capital Territory, and then we did a huge record linkage study, and then classified in individuals who were actually in homes that had high, were measured to have high levels of asbestos exposure. And then there ended up being 7 men who had mesothelioma, and then the expected was 2.75. It's here. So then we can do a Poisson test comparing the observed 7 with the expected 2.75, and then we find that there was a 2.5 times increased risk from living in homes with raised asbestos exposure with this confidence interval. Right, moving on to thinking about selection bias. So, if the aim of the study is to derive from an available subset of patients, and we're thinking about patients, statements about their patterns of survival, which are generalizable to a wider body of patients. However, selection bias may occur when patients treated at a given clinic are not representative of a general class of patient. And it could well be that you might have a specialist clinic which is more likely to treat seriously ill patients. So that means since a patient is treated at a general clinic or a specialist clinic may not be representative of all patients. Selection bias can also occur when treatment is assigned based on characteristics of the patients, thereby precluding comparisons between treatment groups. As an example, patients may be treated more aggressively if they are generally healthier than those patients who are treated conservatively. As an example here, for men diagnosed with localized prostate cancer, radical prostatectomy may be chosen more frequently for men who have, because this is fairly advanced surgery, that they may be healthier than men who are put on to watch for waiting, which is basically we're waiting to see if the disease progresses. As a second example, bone marrow transplant and high-dose chemo versus conventional therapy for women diagnosed with advanced breast cancer, with a high-dose chemo accompanied by transplant involves harvesting bone marrow or stem cells from a patient prior to chemotherapy. The patient then receives high-dose chemo, which adversely affects their bone marrow. After chemo, the stem cells and bone marrow are replaced with the hope that the drugs have killed the cancer cells, and the bone marrow was breast cancer.